everyone, I'm Sujin Kim from Seoul National University, and I'm a graduate student advised by Professor Ho Sung-hwan. Today, I'm going to present my research on searching for dark structures, a comparison of weak lensing convergence maps and lensing weighted galaxy density maps. So this work is submitted to APJS and is currently under review. Dark matter makes up about 85% of the total matter in the universe. Understanding the similarities and differences in the distributions of dark matter in galaxies is crucial for reconstructing the cosmic web and understanding the structure formation. Since galaxies generally trace dark matter due to gravitational effects, we expect a correlation between their distribution. To observe this correlation, we need to map dark matter independently of galaxies. However, since dark matter cannot be directly observed, we rely on gravitational lensing, a technique that measures the bending of light due to gravitational potential without assuming hydrostatic potential, hydrostatic equilibrium. So many people use this method to reconstruct the total matter distribution of the universe. So in this work, I compared the dark matter distribution reconstructed by weak lensing and the observed galaxy distribution to examine their similarities and discrepancies. Especially, I focused on identifying regions with abundant dark matter but relatively few galaxies, which I call dark structure. So a dark structure represents a local deviation of galaxy bias or dark matter-dominated systems. And dark matter-dominated systems are an ideal target to study the dark matter's existence or its properties because it can probe dark matter with less contamination of visible matter, including galaxies. For example, a dark galaxy is one example. It is a galaxy-scale object composed primarily of dark matter with little or no visible stellar content, predicted by most cosmological simulations known as missing satellite problems. And another example is the dark core, which is larger than a dark galaxy. It was detected in a galaxy cluster Abel 520 through weak lensing analysis. It showed a concentration of matter with no bright galaxies, which is unusual in a merging galaxy cluster. It was studied extensively in the context of dark matter because its existence may pose a challenge to the standard cold dark matter paradigm. We can see that dark matter-dominated systems are an excellent target to study dark matter. In this research, I extended this search to the larger scales to find the dark matter, to find the dark structure candidates in the universe. So the term dark structure is defined in this research is a concentration of matter spanning a few megaparsecs, predominantly composed of dark matter with a relatively low galaxy content. Studying dark structures will give a new insights into the nature of dark matter and its interaction with baryons. So my research aims are to find the overall correlation between the distribution of dark matter in galaxies and to identify dark structure candidates and to assess the validity of these candidates through further analysis. Now I will introduce the weak lensing convergence, kappa, which is defined by this formula. For a single lens plane and a single source plane, convergence represents the surface mass density in the lens plane normalized to the critical surface mass density. By measuring the distorted shape of background galaxies, we can generate a total mass distribution map of foreground lens objects as a convergence map. For multiple lens planes and multiple source planes, we can write convergence in this integral form. And delta here is the matter density fluctuation, and Q is the lensing efficiency or lensing weight. And PS here is the redshift distribution of source galaxies. You can see that the convergence is the weighted sum of the projected mass density along the line of sight between the observer and the source. And the lensing weight is determined by the relative distances between the source, observer, and lens. And this is the convergence map that I used for this research. Now I will explain more about the lensing weight. And here's the observer, and here is the source galaxy. And if there is a lens object between them, such as dark matter halos or the galaxies, the light from the source galaxy is bent, and the image of source galaxy is distorted. And this lensing effect has an efficiency that peaks when the lensing object lies halfway between the observer and the source. If the lens is too close or too far away from the observer, the lensing efficiency decreases. And for the real universe, there are multiple lens planes between the observer and source. And among them, the central one contributes the most. Thus, the weak lensing convergence represents the total matter distribution mainly contributed by the central lens plane. For this study, I used weak lensing convergence maps reconstructed by Jeffrey et al. 2021 using dark energy survey year 3 data. They used several reconstruction methods, including linear filtering and the glimpse algorithm. These maps shown here highlights the matter over density in red and under density in blue. The convergence is estimated using a maximum a posteriori estimate as the peak of the posterior, and the posterior is computed by the maximum from the Gaussian likelihood of the observed shear field here, and the assumed prior distribution of convergence. And each reconstruction method used a different prior. And here we use the Wiener and glimpse map together. They are used separately for the full analysis in parallel and cross-match it at the end of the dark structure candidate finding procedure. From this approach, the two maps complement each other. And each reconstruction provided 4 different maps from the 4 different sets of source galaxies by dividing them into the redshift tomographic beams. And here, the source redshift distribution of each beam is shown in black histogram, and the corresponding lensing efficiency curves shows in the red line. And which highlights the different contributions of the lens planes to the total convergence map. So for example, the beam 1 convergence map is reconstructed from the nearest source galaxies, and its lensing efficiency peaks at the redshift 0.165. So the beam 1 convergence map primarily represents the matter distribution at that redshift. For comparison with dark matter distribution, I introduced the galaxy convergence, kappa G here, which is an analogy of weak lensing convergence derived from the galaxy mass fluctuation, delta G. So the galaxy convergence is the predicted convergence only from the galaxy distributions. I used the galaxy catalog, DSY3 Gold catalog, to count the galaxies in each 3D spatial beam and constructed the galaxy density fluctuation maps for each redshift plane. And from the source redshift distribution and lens galaxies photometric redshifts, I computed the lensing weight. Then by this formula, I constructed the galaxy convergence maps like this. So the resulting map is a direct counterpart to the weak lensing convergence map. Now I will show you the main results. First, as expected, the weak lensing convergence map here and the galaxy convergence map here show a strong correlation. And here, this is a product map of 2 maps, highlights the correlated regions in yellow and the anti-correlated regions in purple. You can see the yellow regions are more significant than the purple regions, which shows the galaxies are generally follows the dark matter. And also, this figure shows the scatter plot of kappa versus kappa G for the full footprint, and this shows the linear relationship between over the full footprint. So this indicates the galaxy convergence maps generally follow the weak lensing convergence maps as we expected. And to identify dark structure candidates, I subtracted the galaxy convergence from the weak lensing convergence maps and obtained the residual maps. I applied 3 sigma clipping to identify outlier pixels in each residual maps and grouped them with adjacent pixels. I also applied several selection calcs to exclude small and noisy peaks. Finally, I cross-matched the identified peak regions between the Wiener and glimpse map comparisons. And after some visual inspection, I got the final catalog of dark structure candidates. It contains 22 candidates, and 7 of which appear to be the most probable. And now I will show you an example of a dark structure candidate. Here, the weak lensing convergence map in the left highlights the matter over density in the selected region in yellow. However, in the galaxy convergence map, you can see the galaxy under density in the selected regions. And this red line shows the boundary of dark structure candidate that I found in this research. And as you can see in this residual map, this is the residual map of kappa minus kappa g. You can see the yellow signal, which highlights the relatively higher dark matter than galaxies. And I also estimated the signal to noise of this ratio of this residual signal, which shows also high. And I estimated the integrated signal to noise ratio of this dark matter dark structure candidate, which exceeds 3. And to assess the observational bias, I checked the DSY3 I-band depth map here. And I found that the candidate region is rarely observed as in nearby areas, so there is no significant observational bias. Additionally, I checked the radial surface number density profile of galaxies in a ratio plane of this dark matter candidate, dark structure candidate. It does not show a significant increase toward the candidate center here, candidate center, suggesting a real discrepancy between dark matter and galaxies. The radial extent of dark structures corresponds to the scale of a few megaparsecs, so I think it corresponds to the scale of galaxy groups or galaxy clusters. So now, what are those dark structures? Dark structures can be a high mass to light ratio groups or clusters, or it may be composed of dark galaxies or dark cores, or they may appear as a weak lensing mass peaks because of the line of sight filament with few galaxies. However, in the general lambda CDM context, such dark structure are not readily expected. Therefore, we need targeted observations to further validate these candidates with refined methodologies. For example, we need a deeper observation to perform a detailed weak lensing analysis to confirm these dark structure candidates and to find more faint galaxies. This work is a pilot study to develop our methodology for comparing the weak lensing convergence map with the observed galaxy data. So the methodology can be applied to future light surveys such as LSST, Euclid, and Roman to identify more plausible dark structure candidates and to further investigate their physical origin. Thank you for listening to my talk, and here's the summary slide.
Thank you. Very interesting talk. Okay, so question?
Thank you for the very nice talk. I was wondering if you have any chance to measure the physical quantities of these dark structures, including mass, physical extent, such like that.
Thank you for a nice question. I was also wondering about the dark mass content of these structures, but unfortunately, in this work, I just used this dark matter weak lensing convergence maps, but I didn't perform any mass estimates using the shear estimated shear from the dark energy survey, because the dark energy survey made this kind of weak lensing maps for their cosmological analysis. Maybe I can do a detailed mass estimate through further observations. And also for the size, I just measured the size of this dark structure using just from this radial extent and in the sky, and also the effective redshift of the lensing efficiency peaks here, like this. So maybe it will be performed better if I conduct my own weak lensing analysis for this dark structure candidates.
Very nice talk. As you mentioned, that there's the variation of the mass to light ratio is expected, right? In some regions, due to some astrophysics or whatever, some region mass to light ratio is high, some region mass to light ratio is low. So I wonder if the structure you selected is just the tail of this distribution of the mass to light radiation, or something really unusual deviating from this distribution.
Oh, thank you for a nice question and comments. Yeah, maybe I can expect something like that. In my knowledge, I think that for the galaxy groups, it is not that well established mass to light ratio for the galaxy groups. So maybe the dark structure can be the high mass to light ratio groups, but I think I need to do more further validation.
But you have data, right? So you can check the distribution using your own data.
Yeah, but I have no mass estimates for these dark structures, so I cannot.
I mean, okay, we invent things, to galaxy density ratio.
Yeah.
So what is the actual scatter in mass to light ratio? What is the actual scatter? Yeah, in terms of mass to light ratio. Because you are finding variation in the mass to light ratios, basically, right?
Yeah,
Yes,
that's
I
right.
want to know the actual scatter of mass to light ratio.
Maybe the scatter plot represents something like that. So the kappa is the mass, and kappa g is the light. Actually, it's the galaxy count, not the light. But yeah, you can see a large scatter in this blue or gray dots. So I think there is a large scatter. So maybe I should study about this kind of more scattered.
Is that in logarithmic scale? Or?
Yeah.
Is that in logarithmic scale? Or what the unit?
It's just a linear scale of kappa.
Oh, okay, linear. Okay, bye guys. Many hands.
Sir, yeah, it's a bit technical. So the kappa G is noisy. Have you explored weighting by magnitude or stellar mass?
Yes, thank you for the question. Yeah, I have explored to rate this kappa G using the intrinsic luminosities of galaxies, but I have need the redshift estimates from the photometry. So there are a large uncertainties to use the intrinsic luminosity as a true stellar mass proxy, and also to use the photometric redshift to estimate the intrinsic luminosity. So I tried a lot, but I think there is more bias in the estimates, so I just used the galaxy count, more simple one.
Okay, so I think we have to move on. Let's thank Suji again.